Math 2414 sequences, video 5, types of divergence. This video will go a little bit more into divergence than most books and most teachers will. They'll usually just mention divergence as an idea and not really focus on the fact that there are two distinct types of divergences. Of course, divergence is going to be the opposite of convergence. Convergence being when the values in a sequence progressively get closer and closer to some fixed limit. And there are some sequences where they'll actually reach that limit and stay there for the duration of the sequence. But to contrast that, we're going to look at two types of divergence. And to do that, we're going to consider these two sequences. Let's start by looking at this sequence right here. This one. All right, so if we consider the sequence an equals n squared plus 1 over n, there's a variety of things that we can do. The most common thing, of course, is to take the limit, which we really haven't talked about whether or not you can do the limit like we normally do in a Calculus 1 class. The short answer is usually, as we'll see when we get to the video about theorems on limits, which will be the next video in this series. Actually, that'll be 2 videos later. But regardless, let's just take a look at this sequence for a second and see if we can make some sort of real quick observation. If you're not told where the sequence starts, you just assume it starts at 1. If we put 1 into n squared plus 1 over n, we get 2 over 1, which is 2. If we put if we put 2 into n, we get 5 over 2. Let's just go ahead and write that as 2.5. I know what some of you are saying, you said don't use decimals. Well, since we're comparing numbers, it'll be easier if we just look at their decimal equivalents. If we put in 3, we'll get 10 on top of 3. 10 over 3 is 3.3 repeating. If we put in 4, we'll get 16 over 4, which is 4.25. If we put in, let's scoot me over a little bit. If we put in 5, we'll get 26 over 5, which is 5.2. If we put in 6, if we put in 6, we'll get 37 over 6, 6.16 repeating. I think that's enough for this one. So what's happening to these values right here? Well, they don't start out very large, but they seem to be getting larger and larger and larger. How large will they get? Well, I'm going to argue that they're going to get infinitely large. And one way to make that argument is to actually take the original sequence. Second, get ready to highlight it. Take the original function and do just a little bit of algebraic smoke and mirrors. Anytime you see a fraction with a single term in the denominator, you should always ask yourself, is there a benefit to splitting this into 2 fractions? In this case, splitting it into n squared over n plus 1 over n. And the answer is, well, if something reduces, then yes, there is a benefit. In this case, the first term reduces to n, and the second one stays 1 over n. Remember, what we're essentially asking is what happens as n approaches infinity? Well, I know what happens to the fraction. Fraction will approach 0, but this guy will approach infinity. So we've got a couple of arguments to say that this sequence will approach infinity, whatever that means, and we'll define what it means for a sequence to approach infinity. So we would say that this sequence diverges because its values do not settle down to a single value. They just keep getting larger and larger and larger. If you're wondering, can sequences converge to negative infinity? Of course, just drop a negative in front of this sequence and you've got one. Well, let's take a look at the second one, because the second one's a little bit stealthier. And if you notice, it has an alternator, the -1 to the nth power, which means that as we start putting in progressively larger values of n, the signs will oscillate between positive and negative. So let's see what this sequence is. If we put in 1, we're going to start with -1 to the first power, which is -1. So our first term will be negative. And if we put 1 into the fraction, we get -1/2. If we put in 2, we get -1 squared, which is positive. And put 2 into the fraction gives us 2/3. We put in 3, -1 to the third is negative, and we get -3 fourths. If we put in 4, negative 1 to the fourth is positive 1, and then we get 4/5. The next one, it's easy to pick up on the pattern now. Next one will be negative 5/6, and then positive 6/7, negative 7/8, positive 8/9, etc., etc. So, does it look like these values are settling down to one particular result? And the answer is not really. Well, one thing that's a giveaway is that they're alternating. Sorry, folks. Pause this just for a second. Sorry about that. I had a phone call from a family member. All right. So we were looking at this bottom sequence, and we've noticed that we've got some alternating values between negative and positive, but are they converging to the same thing? And the answer in this case is no. One way that you can tell is to look at what's called a subsequence, something that we'll define here in a little bit. But a subsequence is exactly what it sounds like. It's just part of a larger sequence. If we start by looking at all of the negative terms, negative 1/2, negative 3/4, negative 5/6, negative 7/8. Notice that these, if you ignore the negative for a second, these fractions are getting larger, and they're actually getting closer to 1. You can tell they're getting closer to 1 because the numerator and denominator are only 1 apart. But that difference of 1 is becoming less and less significant because the denominator is getting larger and larger. Think of it this way. You took a pizza and cut it in half and took one of them, or a pizza and cut it in fourths and took all but one of them, and then took a pizza and cut it in eighths and took all but one of them. If you keep doubling the number of slices, and I'm not going to, well, you get the picture. If you keep doubling the number of slices and take all but one of them, you're getting closer and closer to taking the whole pizza. And that's really what's happening with these fractions of blue. So it looks like these blue fractions, the negative ones, negative 1/2, negative 3/4, negative 7/8. In fact, that's approaching negative 1. But what happens if we take the positive fractions? 2/3, 4/5, 6/7, and 8/9. 2/3, 4/5, 6/7, 8/9. Using the same argument, although I would cut a pizza into an odd number of slices, and I skipped negative 5/6. I knew something was wrong there. That's because I was still thinking pizzas that you wouldn't normally cut into 6. But anyway, the positive fractions are also approaching 1, but positively. So we have these two sequences battling out. Every other term is creating a sequence that's going somewhere different. The blue terms that are negative are getting closer to negative 1, and the pink terms, which are positive, are getting closer to positive 1. In order for a sequence to converge, the whole sequence has to go closer and closer to a single value. But in this sequence, half of it's going one place, half of it's going to another place, and those places are different. One's going to negative 1, one's going to positive 1. So what does that mean in terms of the convergence of the sequence? Well, what that means is it doesn't converge. And in fact, I never actually said the top sequence diverges, so let's say up here, the sequence diverges. Doesn't settle down. This one diverges, but for a different reason. It doesn't diverge because the terms are getting larger and larger. It diverges because some of them are going to one place, some of them are going to the other, another place, and those two places are different. So let's categorize what we mean by different types of divergence. The first is called infinite divergence, which is exactly what it sounds like. It's when a sequence gets infinitely large. Now, there is a rigorous definition for it, but first I want to show you the quote-unquote limit definition. This sequence has infinite divergence. If the limit as n approaches infinity, an equals infinity or negative infinity. In other words, as a limit problem, it just blows up either positively or negatively. But there's even a better definition than that, or rather I should say a more rigorous definition. Some people would say that what I'm about to write is not a good definition, but from a rigorous mathematical perspective, it is the definition of infinite divergence. So let's start by saying we have a sequence that diverges to infinity. This means we're about to use some more Actually, I'm not. For any m greater than 0, there exists capital N greater than 0, such that little n is greater than big N implies that AN is greater than M. What does all this mean? This means if you pick any number, doesn't matter how small or large, I can get the sequence bigger than that as long as I go out far enough. As long as my n's hit a certain point and go beyond it, my little n's, then every term of the sequence will remain larger than whatever boundary I set. So if m were 1,000, then if my sequence goes to infinity, then if m were 1,000, then at some point in the sequence, I would go beyond 1,000 and stay above there. Or 1,000,000, or above 1,000,000,000, it doesn't matter. That's what it means to approach infinity. At some point, no matter what finite value you pick, your sequence will surpass that and stay above it forever, no matter what boundary you set. That's technically what it means to have infinite divergence. If we said negative infinity, it would be pretty much the same thing. If we said negative infinity, then it would be AN is less than M, and it would be M less than 0. So for any negative number, we could go far enough in the sequence that we go beyond that negative number. All right, so that's infinite divergence. But the other one is not on the screen yet. It'll be there in a second. The other type of divergence I've named myself. I haven't seen it called this, but I refer to it this time, called oscillatory divergence, or oscillatory divergence. Oscillatory is a root word, being oscillate, like a fan that goes left and right and then left and right. That's what it means, oscillate. Oscillatory divergence is when your sequence does not explode, but parts of it go one place and parts of it go another. In order to discuss this, we have to first define a subsequence. So consider a sequence AN. And again, I'm just using that generic notation, function notation, instead of subscript notation. Then any subset of N is called a subsequence, provided the order is preserved. What do I mean by that? That just means you can't rearrange the order of your terms. For example, if we go back to the first example, which I erased all of, so forget that. For example, if we had a sequence, let's just take a real simple sequence. Let's take a sequence that, let's say AN equals 3n minus 2. You've seen that before. So our sequence goes 1, 4, 7, 10, 13, 16. Yeah, that's right. Slope of 3. Yeah, that's right. Then one subsequence could be all the odd numbers. 1, 4, 7, 13, or in this case, it's every other term. Or I can make a subsequence by taking the first 2, skipping the next one, taking the next 2, skipping the next one, So really, but I got to keep the numbers in the same order they were before. So that's the loose definition of what it means to be a subsequence. There's a more rigorous definition, but I don't think I want to push it that far right now. All right. So what does it mean to have oscillatory divergence? What it means is, inside the text box, there we go. If a sequence has 2 different subsequences, all right? Yeah, 2 different subsequences that converge to L1 and L2 respectively, and L1 does not equal L2. I know that says equal, but I'm going to have to draw that. So, but the slash will disappear when I go back into the text box, but it will come back out when I get out of the text box. All right, if a sequence has two different subsequences that converge to L1 and L2 respectively, and L1 does not equal L2, then the sequence has divergence. In the back of my mind, I'm wondering if this type of divergence is separate from infinite divergence, and something is telling me no. But let's not try to go concoct situations where a sequence on its own goes to infinity, but also has two convergent subsequences. The point I'm trying to make is if you can take part of a sequence that goes to one place, part of a sequence that goes to another, then you have what I call oscillatory divergence. So you can't converge because part of you is going to one place, part of you is going to another. We saw that. Let's get out of the text box. We saw that in the first example. Excuse me, the second example, where in this sequence down here, we'll highlight it. Yep. Half the terms were going to positive one, half the terms were going to negative one. And what I'm about to show you wasn't originally part of this video, but I was wondering, is it possible for a sequence to have infinite divergence, but at the same time oscillatory divergence? In other words, is it possible for a sequence to get infinitely large, but at the same time have some convergent subsequences in different places? I'm going to fiddle around with Desmos just for a second. If you're tired of watching the video, you can stop watching. But let's just go ahead and into Desmos. I got to log in. We're just going to go right to the graphing calculator. All right, so the function I had in mind was, first I was thinking x sine of x. You all know what sine of x looks like. It looks like that sine wave. But the number in front normally represents the amplitude. The amplitude is twice as big, but a 1/2 is half as small. But what if the amplitude was increasing and I put an x? The problem with this is it doesn't go to infinity because, and again, if we zoom out some more, it's always oscillating between getting higher and lower back and forth. Crazy there. Whoa! Or we can't see it. So let's do something else. Let's make it I want to make it positive. So I guess, well, there's a few ways to always make something positive. One way is to square it. So let's just, hello. Fiddle with the settings here. Let's keep the x values relatively short. Let's go 0 to 10. And let's see what the y values do. Y values need to be a little bit higher. Y values up to, I should catch it all. X values. I mean, to 100. That should allow us. Okay, it's going to go higher after that, as we see. And let's start doing some zooming here. So if you'll notice, wave of this sine wave, this squared sine wave, progressively higher and higher. So we could argue that, actually, you know what? This is a really crazy sequence, and here's why. See the peaks of all these? That I wanted to. Well, let's just put it this way. I could pick points on this graph that go up forever, just pick the peaks. I could pick points that never go too terribly far. For example, if I say y equals 100, see this blue line? It's going to hit an infinite number of times. So I've got this subsequence of this continuous graph really going beyond here. This entire graph, there's a portion of it that goes to infinity, of the curves, if you will, and there's portions of it that will converge to whatever number I want. I can make it y equals 100. Let's put a slider. Let's see. Add a slider, please. Slider, thank you. What I want. Okay. So I can move this line up and down as much as I want, so I'm going very high right now. And no matter where I stop it, it's always going to hit that graph an infinite number of times. So if you think of this whole graph, there's a sequence that goes to infinity, a subsequence. Well, that would be the peaks. But there are also sequences that instantly converge to any value that I want, because this horizontal line will always hit an infinity. All right, so that was not quite the way I wanted it to go, but you know what? Sometimes that just happens. Let's get back to the screen share, whiteboard, and let's just say that you need to know that some things diverge for 2 reasons. They go up, sometimes part of it goes one place, and part of it goes another. And I think it's, we're going to end the video here. I was going to say, and that's a good place to stop, but then I'm just copying another YouTube